Welcome everyone. I'm Professor Richard Holowczak, and this is the Normalization Lecture. If you've been following along on our database development lifecycle, you know that we begin by identifying an organization problem or opportunity. We then gather requirements by interviewing users. Primarily, those requirements deal with the data needs of the organization. Based on those requirements, we create an entity relationship model. That entity relationship model is then converted into a relational model. And yes, once we have our relational model, we can implement this in a physical database. However, this lecture is all about how to optimize that logical data model through a process called normalization. The first thing to understand is a formal definition of what a relation is. A relation is a set of attributes that have values for each of those attributes such that the following 6 things are true. Each attribute must be a single value only. We do not allow multi-valued attributes. All values for a given attribute must be of the same data type, either text, numeric, or date. Each attribute name must be unique, and the order of the attributes is insignificant. It doesn't matter what order we put our attributes in. The order of the rows is also insignificant, and perhaps the most important of these 6, no 2 tuples or rows in a relation can be identical. So write those down, commit them to memory, and let's take a look at a set of attributes with some data, and we're going to ask the question, is this thing that you see in front of you a relation? So, what was the first thing that we had to keep in mind? That under every attribute, we have a single value. If we look under part number, we just see one part number per row or per tuple. Description is just one description here, one supplier, one city, one state, and one price. How about the data type going under each of these attributes? We see that for part number, all of these are indeed just numbers. There's no characters or punctuation or anything here. The same would be true for price. There is no extra characters or anything going on under price. Under the description, supplier, supplier city, and supplier state, these are all text. Yes, there are some numbers in there, but we just consider these to be alphanumeric, meaning that they have a mix of letters and numbers in them. What else is important? The order of the attributes does not matter. And last but not least, the names of the attributes must be unique. So if we look at part number, description, supplier, supplier city, supplier state, and price, all of these names are unique. The last 2 criteria to be a relation have to do with the tuples or rows. The first of which says that the order of the rows doesn't matter, and clearly we can write these. As long as we keep the whole row together, we can mix them up in any order we like. The most important criteria in order to be a relation is that there can be no duplicate tuples, no duplicate rows here. So it may look like some of the data has some duplicates, but if you look across at all of the values, every one of these rows is going to be unique. There's something different when you go from one row to the next. Even here for Hewlett-Packard, Palo Alto, California, the prices are different and the part numbers are different. So sometimes you have to look a little carefully and just make sure that every row is unique. So, the question again, is the following a relation? I would answer yes, because the relation upholds all 6 of these properties. Now a definition. What is normalization? Normalization is a process to detect and remove anomalies from a relational model. An anomaly is just a fancy word for saying you've got some kind of a problem. Something is not right, something is not normal, hence the term normalization. There are 3 basic types of anomalies that we are concerned with. And again, I'll use this same supplier part data to demonstrate. The first type of anomaly is what we call a modification or update anomaly. And this occurs when we want to change one fact in our data, but we end up having to change it in multiple places. So here's the example. We see that IBM appears to be headquartered in Armonk, New York. You can see it a few places. If IBM decided to move from Armonk to Canarsie, we would have to go through, and everywhere you see Armonk here for IBM, we would have to update it. Now, you're probably thinking, what's the big deal? Well, imagine if we had thousands or millions of suppliers or a list of 1 million customers with all of their different address information. We would have to update it in multiple places. So it doesn't really matter how many. The idea is it's one fact. IBM is headquartered in Armonk. We're going to change that to Canarsie, but we have to go and visit multiple rows in order to get that one fact changed. The next example is what we call a deletion anomaly. And here what happens is we go to delete one fact from our relation and we lose some additional information. For example, suppose we wanted to remove the fact that Seagate is selling us this 20 terabyte disk, part number 10010. So this is the fact that we want to get rid of. Seagate no longer supplies this part. Is that all we lose? If we delete this row, if we delete this tuple, we also lose the fact that Seagate's supplier city is Cupertino and the state is California. So we went to delete one fact, the fact that Seagate supplies this particular 20 terabyte disk, but we lose a secondary fact, something we didn't intend to lose, the fact that Seagate is headquartered in Cupertino, California. The third example is an insertion anomaly. And here it's kind of the opposite problem of the deletion anomaly. Here we're trying to insert a tuple, but we need some additional information. For example, suppose that we want to add the fact that Corsair, who is a supplier, they want to provide us with a 1 terabyte SSD, and that part number is 10240. What else do we need? Can we just insert that tuple? Well, it turns out we're missing something. We're missing the additional fact in that we don't have on hand what the supplier city and the supplier state is for Corsair. So again, we go to insert one fact, the fact that Corsair is selling us a 1 terabyte SSD, but we need to also insert some other fact that we may not have right in front of us. So these are the three anomalies. Now, that's kind of a technical definition of anomaly. I think you can appreciate the problem, but even before I started talking about this crazy word anomaly and modification, deletion, insertion, and all that, as soon as you saw this data, probably you got kind of an uncomfortable feeling. And that uncomfortable feeling, I'll bet, came from the fact that you see a lot of what? You see a lot of duplication. You see the same part number and description. Here's the 20 terabyte disk. You see that a bunch of times. Here's this 256 gigabyte RAM card. You see that a few times. You saw before that IBM in Armonk, New York, that appears to be repeating. Hewlett-Packard in Palo Alto, California, that appears to be repeating. So your intuition is correct. When you see a set of data like this, and it's all together in one relation, and you see that data is duplicated, that probably means that there's going to be some of these anomalies. And again, what is the definition of normalization? It's a process to detect and remove these anomalies from our relational model so that we don't have this duplication, we don't have this redundancy. As we go through the normalization process, we will remove certain anomalies from our relations, and I will explain in a few minutes how we do that. As we clean up the relation, we can then say that the relation fits in a particular normal form. Each of our normal forms has a definition, and it essentially means that the relation is free from certain problems. The relation will not have a certain type of problem. The normal forms begin with first normal form, then it passes into second, then into third, and then into something called Boyce-Codd normal form, and plus there's actually quite a few more. For the purposes of this particular lecture, we're just going to talk about first, second, and third normal form. Essentially, as we study our relation, we apply the definition of each of these normal forms, and if we're successful, if the relation and its data meet the definition of the normal form, then we can say that relation is free from certain anomalies. That relation is in better shape than it was before. Notice that the normal forms are cumulative. That means that a relation that is in third normal form is also in second normal form and also in first normal form. So you can think of the relation getting better and better as the normal form goes up. Relation in second normal form is better than a relation in first normal form. A relation in third normal form is better still. What are the general steps that we need to follow when we normalize? Well, you may recall from one of the prior videos or lectures, we have the initial set of relations after we've converted or mapped our ER model onto the relational model. And that's where we basically turn our identifiers into keys and the relationships turn into foreign keys. To normalize, we're going to focus on one relation at a time. We're not going to try to normalize everything at once. We focus on one relation at a time. We're going to identify the key and the functional dependencies, which I'll show in the next slides. Starting with the first normal form, we'll then apply the definition of each normal form. If the relation satisfies that definition, we move on to the next highest normal form. For example, we'll go to second normal form, and so on. However, if the relation does not satisfy the definition of that normal form, then we have to stop, and we will split the relation into two pieces, and we'll begin the process all over again. So I'm going to demonstrate this a number of times. You should be able to see quite a few examples as we go through here. Okay, I just mentioned this idea of keys and functional dependencies. I think by now you probably have heard what a key is. A key is an attribute or a set of attributes that uniquely identifies exactly one tuple or row in a relation. If I point down here to the student ID, we can see that if we know what the student ID is, we can determine exactly one first and last name, address, apartment, city, state, zip code, phone number, and email address. In other words, all we need is that student ID to be able to get exactly one row, exactly one tuple. Sometimes our keys can be a composite, and you'll hear this word quite a bit. Composite just means several things stuck together, and in our case, it means more than one attribute. So for example, if we look up here at this student club, we can see that student ID and club ID together form the key. We need to know the student ID and we need to know the club ID in order to tell what the year joined and role is. So student 101, I guess that's Bill Smith, happens to have joined whatever club CC1 is. I think that's the CIS club. They joined in 2019 as a member. That same student, S101 Bill Smith, they joined the basket weaving club in 2023 as the treasurer. Okay, so we need to know both the student ID and the club ID together in order to uniquely identify one tuple or one row in this relation. So we would say that the key here, student ID and club ID, is a composite key. Key can either be a single attribute or a key can be a composite. The important thing is, before we start the normalization process, we should write down the keys for our relations. Functional dependencies are relationships between the attributes within a relation. We know that from the conversion from entity relationship model to the relational model, we'll have the name of a relation, possibly a key, probably a key, I should say, and some other attributes that came along from the entity. A functional dependency is a relationship among these different attributes. Functional dependency is represented by a determinant, which could be an attribute or attributes on the left, and then an arrow, and then a set of dependent attributes on the right. If you don't have this key on your keyboard to make an arrow, you can just use a dash and a greater than sign. We know what it means. So determinant on the left of the arrow, dependent on the right. If I say A determines B, okay, attribute A determines attribute B. Or said the other way around, a value of B depends upon a value of A. Given A, I can uniquely determine exactly one B. So there's a number of ways to say it, but the meaning is the same. You give me a value of A, I can tell you exactly one value of B. Or in this example, give me a value of X, whatever attribute X is, and I can determine exactly one value of Y and one value of Z. The important trick here is that the key will always determine all of the non-key attributes. So let's look at this employee example again. Employee ID is the key. First name, last name, and job role are the non-key attributes. Every relation in this form has at least one functional dependency, and that will be the key. You put it on the left side of the arrow, draw your arrow, and then list out all of the non-key attributes. This is the easiest functional dependency to write, and it should be fairly automatic. As soon as you know what the key is, you write it down on the left, you put an arrow, and then you write down all of your non-key attributes. Usually, we abbreviate functional dependency by saying FD. So here I would say FD1, this is the first functional dependency that we know about in our employee relation. If we look at this example of the customer relation, we can see the customer ID is the key. And as soon as we know customer ID is the key, we can write it down, put our arrow, and then list all of the non-key attributes. However, in this example, in our data, it turns out that there's another functional dependency. Remember, functional dependency is a relationship between the attributes within a relation. And here, city, state, and zip code have a relationship. If I know what the zip code is, I can determine the city and the state. This is how the US mail gets your mail to you. Here's another example. Here's a course relation with course number, semester, section, year, instructor, and classroom. Here, we need a combination of the course number, the semester, the section, and the year. And taken all together, that will determine the instructor and the classroom. So these are all examples, everywhere you see the arrow, these are all examples of functional dependencies. These are super, super important. Probably one of the most important parts of normalization is writing down the functional dependencies before you do any work at all. So let's practice finding some functional dependencies. Here we have an employee relation. It has an employee ID, a first name, last name, benefits plan, and monthly deduction. As you look at the data, probably immediately you start getting a little sense that something is weird here. You see Bill Smith multiple times, Bill Brown multiple times, Jen Green is once, Alice Green is a couple of times. There's definitely some duplication in here. So the first question is, what should the key be for this employee relation? And once we figure out the key, then we'll figure out the functional dependencies. All right, so the first question, can employee ID by itself be the key for this employee relation? So if we look down the attribute here, we see that employee 101, E101, repeats a couple of times. E102 repeats a couple of times, E103 repeats 3 times. So the question is, if I just give you employee ID E101, can you determine exactly one row? The answer is no. If you say E101, we don't know which of these 2 rows or tuples you're talking about. So employee ID by itself cannot act like the key. Can any other single column act like the key? Think about it before I move on to the next one. Could first name act like the key? No, I see duplicates there. Could last name act like a key? I don't think so. Benefits plan, I see benefits plan repeating. Monthly deduction, I see some duplication there as well. So the conclusion here is I don't think any single attribute is going to be able to act like the key. And if one attribute won't do it, then we're going to have to try to stick it together with another attribute. That other attribute will be benefits plan. If we stick the 2 together, employee ID and benefits plan, we can uniquely identify exactly one row or tuple. E101 plus the benefits plan EPO plus, now we know exactly one row that belongs to. E103 and the vision plan, we know that only gives us this exact row. So how did I determine this? I stared at the data. I tried to look for combinations. Because one column by itself didn't work, I tried to look for combinations of columns that would allow me to pick out exactly one row. Could we have used monthly deduction? I don't think so, because some of the deductions are the same, like dental and vision are both $33, so I don't think that would work as far as trying to use monthly deduction. The first name, probably not. We've got a couple of people, different people named Bill. Last name won't work because we have a few people with the same last name as well, which is common in a large database. So employee ID and benefits plan end up being the 2 that we're going to work with in order to act as the key for the relation. Well, once we have the key, then you know what to do. You write down the key on the left, you put the arrow, and then you list all of the non-key attributes. You're just going to have to get used to doing this. It just happens very naturally. As soon as we know what the key is, immediately we get our first functional dependency. The key determines all of the non-key attributes. That's always going to be the case. What else do we see from the data? We can see that if you just have benefits plan by itself, you can determine exactly one monthly deduction. EPO Plus is always $275, dental is always $33, vision is always $33, Blue Cross is $225, and dental plus is $44. So that functional dependency will always work. If you know what the benefits plan is, you can tell what the monthly deduction is. If you know the benefits plan, you can't really tell any other values. You can't tell employee ID first name or last name. If I give you EPO plus, you can't say anything about who exactly is the employee that has it, because multiple employees have EPO plus. But you can say exactly what the monthly deduction is. Does it work the other way? If you know what the monthly deduction is, can you tell what the plan is? And I don't think so, because we have 2 of our $33 deductions have different plans associated with them. So it only works in the one direction. If you know what the benefits plan is, you can determine what the monthly deduction is. And yes, I used the little minus greater than sign for an arrow here. Is there another functional dependency that you can pick out in the data before I move on? Take a look. Maybe pause the video, stare at the data for a few seconds. Is there another attribute that we could look at where if we know what that value is, then we can determine some other attributes? Okay. If you got employee ID determines first and last name, you are correct. Given one employee ID, like E102, we know that will always be Alice Green. E103 will always be Bill Brown. Yes, it is duplicated, But what we're looking for here is we're looking for a value of employee ID that can determine exactly one first name and one last name. So I think we have it all. We've identified the key, employee ID and benefits plan. That immediately allowed us to write out the first functional dependency. Employee ID benefits plan determines first name, last name, and monthly deduction. We saw that benefits plan by itself gives us the monthly deduction, and employee ID by itself gives us the first and last name. Okay, now it's your turn. We have a new relation here. We're going to call it the student relation. Has student ID, first name, last name, semester, year, and GPA. This one's a little tricky. So I invite you to pause the video, see if you can figure out what is the key and what are the functional dependencies, and then we'll go through them on the next slide. Okay, what could the key be? Well, if we look at the data, it couldn't be student ID by itself, couldn't be first name or last name. See all the duplication here? It couldn't be semester, year, or even GPA, right? So all of these repeat. So no single attribute will allow us to act like a key. If we bring the student ID together with maybe semester, that might work, but we can maybe see a case here where I guess S102 has 2 fall semesters in here. So I don't think that that will work. If we bring student ID, semester, and year together, then we can determine the GPA. So student ID, semester, and year, that will guarantee us a unique tuple. S102, fall 2021, there's only one row that matches that. S103, fall 2021, there's only one row that matches that. So our composite key will be student ID, semester, and year. As soon as we know what that key is, we can write down the first functional dependency. Student ID, semester, and year determines first name, last name, and GPA. And what else did you notice? You probably noticed that student ID by itself determines the first and last name. So that's pretty much a guarantee. So a second functional dependency here would be student ID determining first name and last name. Finding the keys and functional dependencies can kind of be like a mystery, sort of. You kind of have to really explore the data and really try and look at almost every data point to try to figure these out. Sometimes we're given data and asked to define the key and functional dependencies. Other problems or other types of normalization problems, the key is already given to us, and sometimes even the functional dependencies are given to us. So it all depends on how the problem is set up. Okay, we've done enough background work. We're going to follow this process where we're picking on one relation at a time. In this case, I'm going to call it the supplier relation. We're going to figure out what our key and functional dependencies are. We're then going to go through our normal forms, and I'll introduce the definition of each of the normal forms. So here's our first problem. Given the coffee shop supplier relation here, determine the key and functional dependencies, and then normalize to second normal form. So again, I invite you to pause the video, take a look at the data, and make sure that you understand where the duplication is, and maybe start thinking about what the key and functional dependencies might be. All right, can product ID act like the key for this relation? And we immediately see no, that there is some duplication, so that's not going to work. How about supplier ID? Can supplier ID do it for us here? No, it looks like we also have some duplication here in supplier ID. Description, definitely not. And cost, it looks like we have cost that gets repeated quite a bit. So no single attribute can act like a key. What did you guess? Product ID and supplier ID together can be the key for this relation. So again, we're going to start off, we'll have a composite key. We don't always have a composite key, but here in this example we do. So product ID is our supplier ID. What can we do immediately? See if you can guess the next step. As soon as we know what the key is, we can what? We can write down a functional dependency. Sometimes you'll see in some books, they'll write out a functional dependency like this little graphical format. A line that goes up means these are the determinants, product ID and supplier ID. And then description and cost are the dependents. So given product ID and supplier ID, we can determine the description and the cost. And we always get that because once we know what the key is, we can determine the non-key attributes. It should be automatic. As soon as you get the key, write it down, put an arrow, and then write out the non-key attributes. But is there another functional dependency? You've probably already figured it out by now. Yes, if we know the product ID, we can determine the description. I suppose given this set of data, it might be possible. No, it doesn't look like it. Sometimes students will ask if the description can determine the product ID, and I think for some reason there's a difference here, right? So if I said 0.5 liter espresso machine, you wouldn't be able to tell me whether it's P1022 or P1026. So it only works in this direction. Given a product ID, we can determine the description. I think that's it. Given cost, we can't really determine anything. Given description, we can't really determine anything. And we already talked about supplier ID by itself. We can't really determine anything. If you tell me S104, I can't tell you exactly one of anything, really. Okay, so that's it. It's a fairly simple problem then. We have the key and the two functional dependencies. All right, now we get to the actual normalization process. I realize it's taken me almost a half an hour to get here, but all of that setup is very important, and I hope that you approach all of your normalization problems this way. The first normal form definition is basically to say that this set of attributes and tuples that you see in front of you, as long as it meets all 6 of those criteria, then it's a relation. If it's a relation, it's in first normal form. It's kind of silly. You're asking if the supplier relation is a relation. Yes, that's the case. So we know we need those 6 things. The names of the attributes have to be distinct. The order doesn't matter. The values underneath are single valued. We can see all of that. And the values are of a common data type. Product, they all start with P and then they have some number after it. Description is all alphanumeric. Supplier ID, similar kind of thing. And cost is all numeric. As far as the tuples are concerned, we see that the order of tuples doesn't matter, and we have a well-defined key, product ID and supplier ID, that's going to guarantee that our tuples are unique. Oh, I think I left one off, isn't it? Yes, the attribute values are atomic. They're single valued. Only one product ID, one description, one supplier ID, and one cost. Okay, so hopefully you've satisfied your curiosity. I've satisfied mine that the supplier relation is indeed a relation. It meets all 6 criteria. Therefore, it's in first normal form. Great. Now we can move on to second normal form. A relation is in second normal form if all of its non-key attributes are dependent upon all of the key. This is a very confusing sentence. The first 19 times you read it, you'll be very confused, and that's understandable. If we look at our relation, we notice that some of the attributes make up the key, product ID and supplier ID. We say that these are the key attributes. That leaves description and cost as our non-key attributes. So a relation is in second normal form if all of these non-key attributes, these description and cost, are dependent upon, and I'm pointing at the arrow here, all of the key. That means description and cost must be dependent upon all of the key, product ID and supplier together. Let's look at a couple of examples. A partial key dependency only occurs in relations that have composite keys. And it happens when we have part of the key determining a non-key attribute. It could be any portion of the key at all. So here's an example relation R with attributes A, B, C, D, E. I've defined the key as AB, which means the non-key attributes are C, D, and E. So imagine that I give this to you. The key is A and B. Then you immediately know that A and B determines C, D, E. The key, AB, determines all of the non-key attributes, C, D, E. But what if I also told you that A by itself determines C? Is A the entire key? No. A is only a part of the key. Hence the term partial key dependency. A part of the key determines a non-key attribute. Doesn't matter how big our key is, whether it's 2 or 3 attributes, if any part of the key determines a non-key attribute, then we say it's a partial key dependency. Here's another one. EF determining GH, G determines H. That's not a partial key dependency. Why? Because E by itself or F by itself don't appear on the left-hand side of an arrow. This is a different type of an issue. How about this one? M and N determine OPQ. And we're also told that O determines M. Is that a partial key dependency? The answer is no, because O is not a part of the key. Even though M is, that doesn't apply in this situation. We're only interested in a situation where M or N by themselves would be on the left-hand side of the arrow. And here's a fourth example. RST determining U and V, and then we see just S and T determines a non-key attribute V. So this is also a partial key dependency. You're looking for any situation where any part of the key appears by itself on the left-hand side of the arrow in a functional dependency. So Y determining Z is a partial key dependency, ST determining V is a partial key dependency. A determining C, or if it was like B determining D, or B determining D and E, anytime part of the key appears to the left of the arrow. So these are bad things. We don't like these. They indicate that there's a problem with the data. So what do we got? Product ID and supplier ID determine description and cost. But we also saw that product ID by itself determines description. This is going to be a violation of second normal form. Everywhere product ID and supplier ID go, they should go together. We should never be able to peel off one or the other by themselves. And yet that's exactly what happens in functional dependency 2. This is going to cause a problem. I put the red box around it. Is the supplier relation in second normal form? The answer is no. Supplier relation is not in second normal form because description is a non-key attribute that is dependent upon, that's the arrow, part of the key, product ID. That's the problem that we have. If we go back to the set of steps, we wrote down the key and functional dependencies, and then we started applying our definition. Supplier is in first normal form because it meets all the criteria for being a relation, but it is not in second normal form. We didn't get there. We failed the test, if you will. So supplier falls back to first normal form. We say supplier, you're in first normal form, but no higher. You're not in second. You didn't make it because you failed this test. Whenever we get into the situation where we apply the definition of a normal form and we fail to do so, we stop. And our reaction is to split our relation into two pieces. This will always be our response. You tried the definition, it didn't work, you failed. Now we split the relation into two pieces. It doesn't really matter what you call them. I just gave them names here so that we can talk about them a little bit. I'm going to call these two new relations products and cost. How do we split them up? Do we just randomly grab some attributes and tear them apart into two pieces? No. We use the functional dependency that caused the problem as a guide. In this case, functional dependency 2 caused the problem, so we're going to use it as a guide. And what do? This formula always works. When you want to split a relation, you copy the attribute to the left, in this case it's product ID, and you remove the attribute to the right of the arrow. Copy what is to the left, remove what is to the right. In this example, we're going to make a copy of product ID, and we're going to remove description. Let's see what these two look like. We came up with our original relation. We saw that there's a partial key dependency. Product ID determines description. So we copy what is to the left. That gives us product ID here. And then we remove description. We bring them down here to their own new relation. Okay, you can already see some of the duplication has been squashed out of it. So this becomes our new relation. How did we know how to split this? We looked at the functional dependency causing the problem. Copy what's to the left, product ID, and remove what is to the right. We bring down description. What's left over? Well, we didn't touch supplier ID and cost. Those were still there. And remember, we made a copy of product ID. So a copy of product ID is left behind. So this becomes our other new relation, which we're going to call it costs. So we take one big relation and we split it into two. Product ID and description go over here in the products relation. Product ID, supplier ID, and cost show up in their own relation. It's very important that we leave a copy of the product ID behind, because if we ever want to recreate the original relation, we'll be able to do so by matching up these two relations on their product IDs. So that's the step we follow in order to do the split. What else happens here? The original supplier relation ceases to exist. It is removed from our relational model. Now we have two brand new relations that we have never seen before, products and costs. So now we have to normalize them. We've taken out supplier, we've put in products and costs, now we continue the normalization process. Let's normalize the product relation. There's only product ID as the key. Product ID determines description is the only functional dependency. Is it in first normal form? We say yes, because we split it from a relation. So when you take the supplier relation and you split it into two, the new relations will also be relations. The new things that you get will also be relations. Is it in second normal form? The answer is yes. Why? Because product relation only has a single attribute as the key. So it's impossible to have a partial key dependency here. In fact, that's a little bit of a shortcut. If a relation is in first normal form and it has a single attribute for a key, then it's automatically in second normal form. So this makes life really easy. Single attribute key, only one functional dependency, you're good to go. You're in first normal form, and you're in second normal form. So at this point, the products relation is normalized. Now let's look at the new costs relation. The cost relation retains the original key, product ID and supplier ID together, and they determine cost. So we can see the combination of product ID, supplier ID together is going to give us the cost. Immediately then, as soon as we know the key, we know that there's the first functional dependency, product ID, supplier ID determines cost. Is this in first normal form? Yes, because the cost relation was split from the original supplier relation. Is the cost relation in second normal form? The answer is yes, because there's no partial key dependencies. Even though product ID and supplier ID are a composite key, there's no other functional dependency to deal with. So we've simplified this to the point where there's no other functional dependency to worry about. So here's another tip. If a relation is in first normal form and it only has one functional dependency, then it's automatically in second normal form. The last step in all of this, it's very important to write down a final set of relations. As you may recall, when we converted from our ER model to the relational model, I asked you to call that an initial set of relations. After we've normalized, we call it the final set of relations. In this case, the products relation with product ID and description, we can see the key and the functional dependency. The cost relation with product ID, supplier ID, and cost. The key is the composite product ID and supplier ID with one functional dependency. Remember, the original supplier relation no longer exists, so we don't even write it down. It doesn't make it out to our final set of relations. So if you were turning this in for homework, this would be what your answer would look like. Here is my final set of relations after I have finished normalizing. Okay, we're coming up on 45 minutes here, so let's look at one more example, and then I think we will finish for this lecture. We have a new relation here. It's called the student-major relation. And of course, right away, you're starting to get a weird feeling because you see some duplication here. So let's dig in. The instructions are, given the student-major relation below, determine the key and functional dependencies, then normalize to the third normal form. So we're going to go a little further this time. The assumption here is that students can only select one major. One major, that's all you get. First up, determining the key. I'm going to invite you once again to pause this video, see if you can figure out what the key is for the student-major relation. All right, did you get student ID as the key? Hopefully you did. Remember, as soon as we know what the key is, we can immediately write down our first functional dependency. Given the student ID, we can determine first name, last name, major code, major name, and major credits. If you tell me S103, that's a CIS major that needs 124 credits, Sally Jones. Only one record, one row, or tuple can be found here. The key always determines the non-key attributes. Is there another functional dependency that we can pick out? And again, I'll ask you to pause the video, see if you can figure out what the other functional dependencies might be. All right, did you get the major code determines the major name and the major credits? Hopefully you did. I don't think we can use name, last name, because there's some Smiths in here. I don't think first name works for anything because there's a couple of Alexes. Probably the major code determining major name and major credits is the way to go. Yes, you could maybe make a case that the major name could determine the major code. I think they kind of determine each other. But the easiest way to think about this is major code determines the major name and the major credits. Yes, we couldn't use credits by itself because a couple of them share, I think, the number of credits. There we go. Major code determining major name and major credits, and I think we're all set up to start the normalization process. First question, first normal form. Is this a relation? Yes, it meets all 6 criteria to be a relation. Names of the attributes, orders of the attributes, the values under an attribute, atomic, and all of the same type. Order of rows doesn't matter, and we have a well-defined key that's going to guarantee that we have unique tuples. So we're all set for first normal form. How about second normal form? Remember what the trick is? What is the trick? If your relation has a key that is only a single attribute, and it's in first normal form, then it's automatically in second normal form. So that's the nice thing about having relations with only a single attribute as the key. You can immediately jump right up to second normal form. So as of now, student-major relation is in second normal form. No partial key dependencies. All right, third normal form. Here's the definition. A relation is in third normal form if it contains no transitive dependencies. Great. Well, you were just figuring out what partial key dependencies are. Now we got to figure out what a transitive dependency is. Let's take a look. You may recall in mathematics, we have something called the transitive property. If A equals B and B equals C, then you can conclude that A equals C. Probably you learned that, I don't know, 6th grade, 7th grade, something like that, definitely in school. In relational algebra, A, B, and C are attributes in a relation. And so we say that if A determines B and B determines C, then we can conclude that A determines C. We would say that A determining C is a transitive dependency. It kind of short-circuits this two-step process. In practice, you're going to look for any attributes, like the B's and C's in this example, that are not part of the key. It can also be more than one attribute, keep that in mind. So here's an example. Our key is W, and it determines X, Y, and Z, and then we see X by itself determining Y and Z. Actually, I shouldn't say X by itself. I should just say X determines Y and Z. Notice that all of this action is happening on the non-key attributes. So this is a transitive dependency. W determines X, X determines Y and Z, therefore W determines Y and Z. Let's look at another example. Here's E, F, G, H. Our key is E and F, determining G and H. E determines H, and G determines H. If we look at the transitive dependencies, E and F determines G, and G determines H. Therefore, this is a transitive dependency. Another example, M and N determine OPQ. O determines M. Here we have a key determining a non-key attribute, and then that non-key attribute determines part of the key. This is not a transitive dependency. Transitive dependency will only occur out here in the non-key attributes. If you said O determined P, or O determined Q, or O determined P and Q, then I would say that's a transitive dependency. But when we cross back over to the key, this situation doesn't really apply. How about this one? R and S determine T, U, and V. And then TU determines V. This is also a transitive dependency. RS determines TU. You can think of those two together. And then TU determines V. Therefore, we know that RS determines V. So that is a transitive dependency. So there's a few different ways we can see it. We can look at single attributes, groups of attributes. We just have to line up what is our A, what is our B, and what is our C, and do they follow this pattern? A determining B, B determining C. Let's look at our student major. Is student major in third normal form? The answer, as you probably guessed, is no. Student ID determines major code, and major code determines major name and major credits. This is the shape of a transitive dependency. Therefore, student ID determines major name and major credits. We already knew that. So we stop. Student major does not meet the definition of third normal form. We have to stop here and we have to fix it. How do we fix it? You're probably already guessing. This is the functional dependency that caused the problem. So we're going to split the student-major relation into two new relations. How do we know how to split it? We use the functional dependency that's causing the problem as a guide. As always, when it comes to splitting, we copy what is to the left, in this case major code, and we remove what is to the right of the arrow, major name and major credits. This always works. You find out the functional dependency that's causing the problem, copy what's to the left, remove what is to the right. Here's the original. We find out that major code determining major name and major credits is a transitive dependency, so we're going to use this as our guide. Here we make a copy of major code, and we remove major name and major credits, and we decided to call that the majors relation. What's left over? Student ID, first name, last name, and the copy of our major code. Remember, we don't remove major code, we just leave a copy behind. Make a copy, leave it behind. If we ever need to bring this together again, we have major code that we can join together on here. All right, now we have two new relations. The student relation has student ID, first name, last name, and major code. We know the key is already student ID. We know that there's a functional dependency, student ID determining first name, last name, and major code, and that's the only functional dependency we have. There's no other way to get any uniqueness unless you have student ID. It's in first normal form because it was split from a relation. It's in second normal form because there's no partial key dependencies. And yes, it's in third normal form because there's no transitive dependencies. It is impossible to have a transitive dependency if you only have one functional dependency. So this will be our final students relation. How about the majors relation? Major code is the key determining our major name and major credits. It's in first normal form because it was split from a relation. It's in second normal form because major code is only a single attribute, so there's no partial key dependencies. And yes, now majors is in third normal form because it has no transitive dependencies. You can't have a transitive dependency if you only have one functional dependency. So this will be our final majors relation. As always, I ask you to show the final set of relations in a separate section. Majors, major code, major name, major credits with the key and functional dependency. Students with student ID, first name, last name, major code with the key and its own functional dependency. These are two separate relations. The original student major relation no longer exists in our model. It's gone. We don't worry about it. And this is what we're left with, these two in its place. I've got about 5 minutes left. A few things to keep in mind. Many relations that you work with will already be in third normal form. If they only have one functional dependency, which we know is the key determining all of the non-key attributes, then you'll automatically be in first, second, and third normal form. So that's something to look out for. If you've done good entity relationship modeling and you have a good way of converting that ER model over to your relational model, more than likely, most of your relations will already be in third normal form. Some relations will be in second normal form, but not third normal form, like we just saw with our students, and then we're going to have to normalize. Some relations will be in first normal form, but not even second normal form, like our supplier, and then we're going to have to normalize to fix it up. Other thing to keep in mind is that there can be multiple violations of the normal form rules. For example, relation R over here, it has a single attribute as the key, which is A, but notice B determining C, D, and E. What kind of a violation is that? That is a transitive dependency. And within that, D determining E is another transitive dependency. So we can have more than one transitive dependency in our relation. Let's look at relation S. Relation S has a composite key, VW determining the non-key attributes X, Y, and Z. W by itself determines X, V by itself determines Z. Here are two violations of second normal form. So S is stuck in first normal form. It has two violations here. Okay, and then let's look at relation T. composite key, FG, determining HI and J. G by itself determines HI, and H determines I. Here we have a combination. This is like the whole thing all put together here. G by itself gives us a partial key dependency. So FD2 is a partial key dependency. And then FD3 is a transitive dependency because H determines I. That's over here in the non-key attributes, H determining I. So relation T has two things that need to be fixed as well. One of them, fix the partial key dependency. The other, fix the transitive dependency. So these are all possible. The important thing to remember, even though you see that there are multiple functional dependencies that are causing problems, always stop at the first problem you see. Don't move on. Don't try and split the relation into 3 or 4 or 5 parts. There's really a chance of missing something when you do that. So just remember, even though you might see that there's a problem with both second and third normal form right at the beginning, always stop at that first problem, split the relation, and then reset and start over again. That's the best advice I can give you for working with these. A final review. First, work with one relation at a time. Don't try and normalize 3 or 4 relations at once, just start with one at a time. Write down the key and functional dependencies, and then go through the definition of each normal form. As soon as a normal form definition is not true, stop and perform the split. Only split a relation into 2 new relations. Don't try and split them into 3 or 4 at a time. Just do one split at a time into 2 new relations. Then, normalize each of those 2 new relations separately. They're new to the model. You have to treat them like you've never seen them before, and you go through the normalization process just as you would any other relation. Finally, it's very important that you show all your work. This includes the reason why a relation does not meet the normal form definition, and what steps you'll take to fix the problem. That is, to normalize the relation. It's important that you show your work, just like in a math class, so that if you do get off track for some reason, it's easier to find out where you might have made the mistake, and we can track it down much more quickly. Okay, I think that's it for this video. Additional notes on databases and data warehousing can be found on my website. Thanks for listening, and I will see you in the next video.